Thanks for inviting me. And okay, so today I'll be talking about not joint work with all the amazing people. I'll be talking about works by Ketan and Forspielke and Visu and his advisor. So okay, and it will be like a light version talk of Avi's Monday talk and Ketan's talk. So just sit back and relax and ask many questions. So the outline is so I'll talk a little bit about invariant theory and say how it connects to PIT. And then I'll show two examples and the two results of Forspielke and Dirks and Makam. And then I'll just talk about open questions and future work. So this will be a more algebraic side of the developments in invariant theory that happened recently. Okay. So again, just the basics again. So if you forgot from Ankit's talk already. So if V is a vector space and G is a group acting linearly on it, a nice group, let's say, we're not going to use finite groups. We're going to use, continuous groups and connected. So let's focus on the second example. V is like the set of matrices, and then G acts by multiplying on the left and right. These are the groups. So an invariant polynomial is a polynomial that doesn't change under the action of G, right? So, by now you all know this. So, for example, in the matrix group here, it is generated by the determinant. And the other object that we are interested in are the orbits, right? So is the set, when you apply all the group operations on a vector V, this is the orbit of V, and in the closures, right? So this is the orbit with its limit points, okay? So it can be characterized by all the zero sets of all the polynomials vanishing on G, acting on V. So now, the basic questions that we have, I guess we've seen them through the past days, is given a vector space V and a group G acting on it, well, we want to say, can we compute the generators of these invariant polynomials? Can we find the relations among these generators? And many other questions, right? Geometrically, we can ask the following question that we have been asking throughout this week, right? Like the orbit closure intersection. Given 2 points of the vector space, do the orbit closures intersect, right? So by a theorem of Mumford, the orbit closures, they do not intersect if and only if there exists an invariant polynomial which witnesses this intersection, which means that it evaluates differently on both points. Okay? So then, suppose that you have a basis for the invariants, right? It suffices to evaluate a generating set of this ring of invariants. It suffices for you to essentially evaluate on a random linear combination of these random invariants, right? You're going to get non-zero with high probability. So this is a way that we could solve this problem by a randomized algorithm. Okay?
This theorem is true only for some specific groups, right?
Yeah, I'm assuming the groups are really nice and I don't want to talk about it. So yeah, I think it was talked about on Monday already and off, right? So, okay. And then the question is, well, how can we deterministically find such polynomials? And is this the only way that we can solve it? Well, by now I think Ankit kind of gave the spoiler, of course not, right? But okay. And in particular, there's an easier problem, right? In Ketan's list of easiest problem, he didn't even mention, write it down, but it's the null cone problem. If I just give you 1, V and W 0, is 0 in the orbit closure of your point, right? So, and now the question is, how do these problems actually relate to PIT, right? Because Ankit gave an algorithm that's completely analytic, but how does it relate to our usual natural PIT? So let's see how it happens. So, okay, what is our input description? I would just give you the group G, the vector space V, and they're given by their natural encoding, right? So if I give you like GLN, I just give you the matrices, right? And of the generators, and V I'll just give you as the coefficients, like the usual vector space representation. Okay, so for example, let's say I have one group GLN and I have matrix V, and then I just give you the matrices and I give my input matrix as an element of the vector space, and the action is clear here, the conjugation action. Okay, now, again, problems of interest, we have the null cone problem, orbit closure intersection. Again, efficiently and, due to Ketan, right, how to succinctly compute the generators of the coordinate ring, and if you can actually do it, and also the orbit closure containment, right, which Marcus talked about and other people also talked about. So, okay, again, a couple of remarks just to reinforce is that the null cone problem and the orbit closure intersection problem, they're witnessed by invariant polynomials, right? So we can solve them by using polynomials, these special polynomials. Now, the orbit closure containment seems much harder, right? And Marcus proved that it's NP hard for the case of tensors, right? So, but examples of orbit closure containment problems is the VP bar versus VNP bar problem, and also like border rank as Marcus talked about. Okay, but for this talk, well, since we're interested in polynomials, let's only study the problems where polynomials appear. Okay, so okay, now so what are the basic structural questions and results, right? I mean, invariant theorists were interested on these questions like since this field started, and one of them is the first, well, is this ring finitely generated, right? And it was the result of Hilbert that yes, this ring is finitely generated. So we have a finite number of generators that we need to find so we can test whether orbit closures intersect or not, right? Can we have complexity bounds on the generators, right? Are these generators hard to compute? And the first question was, well, can we give upper bounds even on the degrees of the generators of the set, right? Because if you had a generator of exponential degree, then you have no hope to evaluate it even, right? So with theorems of Popov and then Dirksen, this improvement, well, you have exponential degree bounds, and as Avi mentioned on Monday, these are tight for many group actions, right? And the other one is, can we construct these invariants in certain generality? And I guess as was mentioned a little bit in Ankit's talk, the answer is yes. You can use the Reynolds operator, and you have ways of constructing them. So you have the Cayley omega that Ketan mentioned, and there's also the Casimir operator. So we have some structure results and some algorithmic results, but they're not that great, right? So for example, the Reynolds operator is very general, but it's not efficient. It does not give you like very nice polynomials to work with. You need something more, as Ankit mentioned a little bit in the end of his talk. So for algorithms, we really, if we want to do PIT, we really need simple invariants, right? We need invariants, I mean, in VP, let's say.
Can you explain what is Cayley omega? One of these, like,
maybe I can explain offline. Yeah, it's a bit, yeah, it's not something within half an hour that I can do and do more stuff.
But
so
it's an algorithm to generate a basis for the invariant ring.
Yeah. Yeah, I can tell you the algorithm later. So yeah, so yeah, and well, I mean, we have exponential degree bounds. So even for restricted cases, if we want to do restricted PITs, like these restricted PITs for null cone and orbit closure intersection, well, we need polynomial degree bounds, right? If we expect to do it in algebraic way. And it's hard to prove better degree bounds even for special cases. So for example, for the operator scaling case that Ankit talked about, polynomial bounds were only proved in 2016 or like late 2015. And before all these works that we talked about with Ankit, the previous algorithms for null cone and orbit closure intersection, they were doubly exponential. Okay, so we want to improve on this thing. So now let's see how PIT appears in our natural way, like the way that we're accustomed. So, okay, I know that we have to talk about separating variants now, but let me just talk about the most basic, yeah? So since it's an introduction. So in GCT5, Momole defined this, the right complexity version of seeing the coordinate ring, okay? Which is this idea of succinct generators. So if I pick a coordinate ring, so this is the ring of all the invariant polynomials for the group action. Okay, we say that this invariant ring, it has, and let C be like a simple circuit class. Okay, think of C as VP. Okay, it has like C succinct generators if there is a small circuit F on the variables V. So V is the variables of the vector space. Okay, so think of x1 up to xn, and Y are some auxiliary variables. Okay. So this circuit here belongs to the circuit class C, such that when I write the polynomial computed by the circuit, okay, can be written in the sum of FIV times GI on the variables Y, so that you can write them in a separate way, where all of these FIs, when you collect this sum here, this set is a set of generators of your coordinate ring, okay, and these polynomials, they're linearly independent, right? So essentially, you want a way to encode all the invariants by a small circuit at once, right? And after Ketan defined this, well, you said if this ring has C succinct generators, then the null cone and orbit closure intersection can be solved simply by solving PIT for the class C. Because remember, there's the theorem of Mumford that if you have two orbit closures, They do not intersect if and only if you have one invariant, right? And here he's giving us a way of efficiently accessing a random invariant. So far, so good? Okay. So again, so to test if a point u is in the null cone is essentially to test if f, when I substitute this v by u, right, this whole polynomial here in the variables y is equal to 0, identically equal to 0. And to test orbit closure intersection, again, I just substitute v by u and v by w here, take the difference, and I do another PIT test. Yeah? Okay. So, well, as a remark, usually if you want to do this again algebraically, you want C to have polynomial degree bounds, right? But the analytic approach that Ankit showed may sometimes not need these degree bounds, right? So for example, the works that Ankit talked about, right? We don't need like polynomial degree bounds. But for orbit closure intersection, like that we don't know, right? So all the algorithms that we know so far, they do need polynomial degree bounds, as we'll see.
Do you also need the fact that it is explicit?
Yeah.
Sorry?
For the orbit closure intersection problems, whatever, do you need also the fact that that categorical quotient is explicit in a relaxed sense? Or
No.
just degree bound?
Yeah.
Oh.
This is a major point of the analytic approach. Maybe
Yeah.
I didn't stress it enough. You don't need to know what are the invariant polynomials. You just
need
know that there exists a one.
Yeah, I know. But when you go to the general representations, I believe this would break down at some point.
I'm not sure.
Yeah, we don't know, but I mean, so far,
That would be great.
like it could, so Ketan, it could be possible that you only need like you can use the Casimir process and you can just get like
For null cone,
properties.
for null cone.
Yeah, for orbit closure
For
intersection
orbit closure
is a different game, but we also don't know. Yeah, it's but even here already shows up. Like for example, for null cone.
For null cone, I'm willing to.
Yeah. Okay.
So, and
So
the
we-
relaxed version would be that these FIs are just separated.
Separating variants in the relaxed sense, yeah. But I just want to keep it simple. Okay, so now let's see two different algebraic examples on how to do PIT for restricted classes of this general problem that Ketan defined. Yeah. So the first one will be the simultaneous conjugation problem. So what is the setup here? So here I have only one group, which is the special linear group. All the invertible matrices determine 1, and my vector space is m tuples of n by n matrices, complex matrices. Okay, and the action is again, I act by conjugating by the same element. Okay, yeah?
The degree bound in the previous slide, if the FIs have large degree, doesn't seem to change your algorithm.
Here?
Because you substitute instead of V's and numbers. So
Yeah.
So the degree bound of Fi doesn't matter also here?
It will be exponential in the size of the circuit anyway, and that's not a limiting problem. It's just the degree of the invariant polynomials that matter.
No, Fi can have huge degree. GI should have small degree. In this, just
Right, yeah, for this, yeah, you're right. Yeah, for this, just the GIs can have small degree.
which is not about the FIs.
Right.
It can be just small circuits. As long as the GI have small degree in Y, this is okay.
I think should be okay.
The circuit has
Yeah.
to compute F. The circuit computes
Yeah, I think what he meant is like the circuit computes F, but like it can be exponential in the degree of the variables V in the circuit could be exponential, and yeah, so this is fine. Yeah, as long as the degree of the Y's are polynomial, I think it should be okay. Yeah. Okay, so back to the setup. So we have the simultaneous conjugation, and again, the null cone problems. I just give you a tuple of matrices, and I want to know if it evaluates to 0 on all the invariants, and the orbit closure intersection. Again, I want to see if there's an invariant that evaluates differently on them. Okay, so for this case, we have a really nice description of the invariants, okay, which are given by Procesi, Razmislov, and Formanek. And we also have degree bounds, so that they were generated by these polynomials. So trace of the products of these matrices, like x1 up to xm. So you pick all the combination, all the words, okay? So think of it as a word of length up to n squared, and take their product, and you take their trace. So all of these polynomials, they generate the invariants for this action. Okay, so this is a really nice description. And Okay, so yeah, we have polynomial degree bounds, and now the question is this set like of generators succinct, right?
That RAS is different from our RAS.
That's Razmizlov. That's Razmizlov. Yeah. It's maybe I should.
I think here it can get confused.
Yeah. Ron Raz is not that old, and Razborov was not that old, I think. So yes.
He did it when he was a baby.
Maybe, yeah. Okay, so for the simultaneous conjugation, okay, so we know these generators, and now how are they succinct? Well, succinctness, in GCT5, and then as Forbes-Spilka also observed, they essentially can be computed by a read-once ABP. Okay, and how do you do it? Well, essentially, pick these matrices like Zj. Okay, so Zj will be the first one like here, and then you put like a fresh variable yj0 for the identity, and then you put yji for the matrix xi. Okay, and once you compute the trace of only this product, z1 up to zn squared, okay, you're going to get monomials here, which, well, we know that they're linearly independent, right, times the trace exactly of this word xi1 up to xil, okay? So it's an easy exercise, and I already gave the hint, so you can fill in the blanks here. So you don't need to get caught up. So essentially, the only thing is that this is a read-once ABP, okay? So how do we solve it? Now we have succinctness, and the succinctness is really nice. And again, by Mumford is enough to check, given 2 points, right, if this circuit is different from 0, right? So, okay, and again, this polynomial is 0 if and only if all the invariants agree, right? Because you have, each of them are encoded by a monomial. Okay, so for Spilka, this is a read-once ABP. Then, by Rice-Spilka, we have a white box PIT in P and a black box PIT in quasi-P. Okay, so since we all know read-once ABPs, I'm not going to go over this proof. I want to go about the next proof, which is a little more interesting. Any questions you can ask Visu, because it's his work. So, all right. So now let's talk about the left-right action again, which is the operator scaling action, right? So here the group is a Cartesian product of SLNs. Our vector space is again a tuple of matrices, and the action of GH is, again, you pre-multiply by G and post-multiply by H. Okay, there's the -1 just because of the group action, right? Okay, so, and then we have null cone and orbit closure intersection, and let's just talk about the orbit closure intersection from now on. Now the invariants, okay, so I put the people who came up with the invariants here, the older people, and then you have the new people that gave the degree bounds, right, and they're very recent. So these invariants, they're generated by these funny looking polynomials here. And what are these polynomials? They're essentially determinants of, so these yi's, okay, for each d, we have a fresh matrix yid, which is a d by d matrix. Okay, so think of this as the fresh new variables that we have. Okay, and we take this determinant of the yid tensor power with xi. Okay, so these are the invariants, and it's enough to take matrices of size of dimension d for d less than or equal to n to the 5th. Okay, so these are the invariants. They become a little more involved than the previous ones, right? And again, the PIT question is, well, A, and I'll put this like not equivalent, and not equivalent is if the orbit closures don't intersect. Okay, A is not equivalent to B if and only if there exists some D, right, such that this polynomial is different from 0, right, where y's are the variables now. Okay, and I substitute the tuple A and the tuple B by x. Okay, and if you want to encode all of it as a one PIT question, just add a fresh variable z, right, to keep track of all the. So, anyways, if you really insist that you need to have one polynomial. Okay. So, okay. So before we talk about the orbit closure intercept, I'm not going to talk about succinctness here. I'm just going to talk about a different approach of solving this problem, okay, which is the Dirks and McComb approach. So now let's first talk about the null cone. What do we know about the null cone? Okay. So okay, and before, let me give a spoiler. So how are we going to solve this action, the null cone problem orbit closure intersection, is by a reduction. There's a polytime reduction from the left-right action to the simultaneous conjugation action. Okay. So this is like, in a very sense, it's a kind of complexity theoretic kind of proof, which was not done by complexity theorists, right? Unless Visu is converting, I'm not sure. So, but before, let's talk about the null cone algorithm, okay? So what do we know about this? Well, we have an analytic algorithm that Ankit just showed, okay? So we can decide membership in the null cone in polynomial time. And again, for this approach, you don't need the upper bound and the degree of the invariance. But there's also an algebraic algorithm by Ivanios, Chiao, and Subramanian, right? That they decide membership in the null cone in poly time.
Excuse me, I thought you need exponential degree bound due to Dirksen, isn't it?
No, we just need finite generation.
So in the previous version we did it, but yeah, in the
Oh, you can get rid of that?
Yes.
Yes. Uh-huh.
The version, in the current version on the archive, you see an analysis that
But
just
can
uses
explain that to me
it.
later.
Yeah. So, okay, so in IQS, they can decide membership in the null cone in poly time. And moreover, they can also find, if A is not in the null cone, they can explicitly find some matrices, y1 up to id, such that, that determinant polynomial, that funny polynomial, is different from 0, okay? So they can find these matrices, and this will be important for us, okay? Okay, so now that we know the null cone, which is a basic subroutine, let's prove orbit closure intersection now via reduction, okay? And this is the works of Dirksen and Visu. So, okay, so suppose that our input is given by matrices of the rational entries, and okay, we know orbit closure intersection for simultaneous conjugation. How can we get this reduction, right? So, okay, this is their theorem, okay? Orbit closure intersection for left-right action is actually equivalent to orbit closure intersection at under polytime reductions, okay? So this is a first reduction in invariant theory, I guess. Well, efficient reduction. There was a less efficient reduction before for people who know quivers. So, okay, let's do the easy direction, right? Like orbit closure intersection for simultaneous conjugation, okay? Polynomial time reduces to orbit closure intersection for left-right action, okay? And this reduction here is very simple, right? So so this equivalence, and if I put SC is under simultaneous conjugation, and the equivalence LR is the left-right action, right? So, okay. So the reduction is just this. So this tuple of matrices, right, is equivalent to this one. The orbit closures intersect under the simultaneous conjugation if and only if, well, I just append an identity matrix here, right, and these orbit closures intersect under this, under the left-right action. Why? Well, because if you look at the identity here, right, like you're essentially forcing G and H to be the same, right? So you have the conjugation action. So that's the proof here. So that's pretty easy. Now, let's go to the hard direction, right? Which is orbit closure intersection for left-right action reduces to orbit closure intersection for simultaneous conjugation. So now, okay, so let's just use some easy facts, right? We can test that the determinant of each matrix AI is equal to the determinant of each matrix BI for all i's. Otherwise, we have an invariant that shows that they're not different. So let's get rid of these cases. And the orbit closure intersection does not change if we replace an input, A1 up to AM, by any other element on its orbit, right? Because we're still talking about the same two orbits, okay? So far so good. These are just very easy facts. So let's see how they do the reduction. So, okay, what is the easy case here? Suppose that one of the tuples that you have, A1 up to AM, is in the null cone, okay? In this case, we know how to test it in polynomial time, so orbit closure intersection is equivalent to the null cone problem. So then we can just use the algorithms and put it in P, okay? Now what is the other easy case is that suppose that my first matrix A1, okay, has determinant different from 0. And remember, the determinant of AI is equal to the determinant of BI, so the determinant of B1 is also different from 0, okay? Then this left-right action here, right, the orbit closures intersect if and only if, let's pick a different point in their own orbits, right? I can essentially use this point here. Notice that I'm just multiplying everyone just on the left by A1 inverse, right? So then I have this point here, which is in the orbit of A1 up to AM, and I have this point here in the orbit of B1 up to BM, right? So these orbit closures are equivalent if and only if these are equivalent, right? But again, we saw before that these orbits are equivalent if I have the identity, if and only if I shrink the tuples, these other tuples are equivalent under the simultaneous conjugation action. Yeah? So that's the easy case, right? And it's easy to adapt this easy case when we have the span of AIs, it has an invertible matrix, and we know the invertible matrix, okay? in the span. So if I gave you like, okay, there's a linear combination, here's a linear combination of these matrices that is invertible, we also know how to do that case. Okay, so let's just assume that and keep going. So what is the remaining case? Well, remaining case is that both tuples, they're not in the null cone and they do not span an invertible matrix. Right? So now, well, what's the plan? The plan is to reduce to this previous easy case. Okay? But for that we need blow-ups. Okay? And what are blow-ups? Here's the definition. So if I have a tuple of matrices, okay, so its kth order blow-up is essentially you take each matrix AI and you tensor it with this elementary matrix that has only a 1 in the JK entry, okay? And you do that for all of the matrices M and all of the JK. Oh, I have 2 Ks. Anyways, for all JKs in the blow-up, yeah? Okay, so it's a lemma from Dirks and McComb that if I have 2 tuples of matrices with rational entries and K is large enough and you can pick one K that you like, so the orbit closure intersection problem. So A and B, their orbit closures intersect if and only if the orbit closures of these blow-ups intersect. Okay? And the blow-up is not that big, right? So you can write these efficiently. Okay, so what is the remaining case? Okay, they're not in the null cone, and
the size of the input is blowing up by k squared in this. I mean,
yes, but k is small, right? So,
yeah.
Yes. So okay, so now, so we know that A and B are not in the null cone, and well, we know that they don't span any matrix. So in particular, these determinants are 0, right? But A not being the null cone, we need. Oh, thanks. So A is not in the null cone. Then we know that there exists matrices, in particular dimension n-1 or even higher, right? Such that this polynomial does not vanish, right? By what we saw in the invariant. So we know we can find these matrices by the IQS algorithm. So in particular, if you look at the n-1 blow up, it has an invertible element, right? And all the other blow ups will have invertible elements, okay? So now let's use this lemma, the Dirks and McComb lemma, to reduce the blown instance to simultaneous conjugation. Oh no, that's it, right? So yeah, my previous cases. So I have a blow up that has an invertible element, and I know how to find an invertible matrix in the span of these blow ups. So remember, if I go to my previous case in the slide here, right, is exactly the other case that I know how to handle, right? Because I'm also given to you the invertible matrix in the span. Okay. So this finishes the reduction, right? So just map them to the blow-ups, and from the blow-ups and the span of the invertible matrix, you can find an instance, a larger instance of the simultaneous conjugation action. Yeah? And then once you reduce the simultaneous conjugation action, you can do the read-once ABP PIT.
So it's really a reduction to either the null cone of left-right
Right.
or to the orbit intersection of simultaneous conjugation.
Exactly, yeah. It's either a reduction to the null cone or to, yeah. So, okay, and now let me just mention a little bit the different algorithm, right? The analytic result, which doesn't go by reduction, right? And since Ankit didn't talk about it, so we can just mention some details here. So we can decide orbit closure intersection in polytime. There's a joint work with Zewan, Ankit, Iwanji, and Avi. And so now for orbit closure intersection here, we do also, just like Dirks and McComb, we also need the polynomial degree bounds. And here's the outline. So Ankit showed us how to scale anything that can be scaled to doubly stochastic, how to scale very close to doubly stochastic, right? So suppose that we could just scale that directly to doubly stochastic, okay? So scaling to doubly stochastic takes us to the element of minimum norm in the orbit closure, right? As Ankit mentioned the optimization problem in his slide, right? Like, and Avi talked about it on Monday. So suppose that V tilde and W tilde, they are the elements of minimum norm that we found in both orbits, okay? So they may not be the same, but there's a result by Kempf and Ness that these orbit closures intersect if and only if these elements of minimum norm, they're equivalent under rotations, okay? And by rotation here, I just mean an action of the maximal compact subgroup, which in our case would be like just products of unitaries. So it's essentially rotations, right? And then we would just need to test if these points, they're equivalent under these rotations. And we have an algorithm for doing that. But a remark, well, analytic approach, right? We only get approximate results for any of these points, and to solve these approximations is very cumbersome, and we had to do a lot of work as opposed to this beautiful reduction that I just showed you. Okay? So it's just one page, and I have 0 minutes. Yeah, sorry.
So elements of minimal norm are canonical elements for orbit closures up to rotations.
Yes, exactly.
And by the way, where did you need that polynomial bound?
We need polynomial bound because of the approximations here. Like we need to get like exponentially closed. So if you had exponential bound, you need to get doubly exponential close to.
You only required 1 over epsilon, is that it?
Yeah.
No. Here you need this algorithm. It converges in log 1 over.
No, yeah, but he said just for the null cone, we just need 1 over epsilon. And here is the difference that now we need to get exponentially close, and we're lucky that we can get exponentially close because of polynomial degree bounds. Yeah. If you had exponential degree bounds, you have to get doubly exponentially close.
I'm just surprised. How could you get even 1 over epsilon with no degree bound?
Yeah, okay, I can explain to you. Since I have 0 minutes or -1, let me just say the open questions. So here's, can we create a complexity theory for these computational problems in invariant theory? Can we have these efficient reductions between like different group actions, right? So, Dirks and McComb showed that, these problems are equivalent, like simultaneous conjugation left-right action. Can we find complete problems? I don't know, right? Like, can we have more applications of these algorithms? As Ankit said, we don't have applications for tensor scaling even, right? And well, what is the difference between analytic methods and algebraic methods? Like, which one is the strongest, right? And thank you, because